House wiring, basic knowledge about electricity. Basic electrical knowledge that everyone should know before wiring a house. To understand wiring and how electricity works in a home, it is important to understand its basic parameters. The electricity is a type of energy that is created by the movement of electrons between 2 points with a potential difference. This movement of electrons, electric charges, is called electric current. Electric current flows through a system called a circuit. The simplest circuit is a no-load circuit containing a power source and conductor. A circuit is a closed path through which current flows in a loop and returns to its source. For current to flow, the following conditions must be met. The current path must be continuous, closed loop. There must be a potential difference between the starting point and the return point. A conductor is a material that allows current to flow easily. This type of no-load circuit is called a short circuit, in which current flows until one of the two components is damaged, which occurs in a very short time. A normal circuit is a circuit with a load that allows current to flow to do work and includes power source, conductors, and a load. If the circuit is open at any point, there is a potential difference between the points but no current flows. When the circuit is closed, electric current begins to flow from a higher potential to a lower potential through the load and returns to the power source. The most important parameters describing the circuit: current, I, the amount of electric charge flowing through a circuit. The amount of current is measured in amperes, A. Voltage, V, the electrical potential difference between 2 points in the circuit that allows current to flow. Voltage is measured in volts, V. Resistance, R, the opposition to the flow of current through a material or other component. The resistance is expressed in ohms, omega. Power, P, the amount of work done by electricity, consumed or delivered in the circuit. Power is measured in watts, W. Electrical circuit with multiple branches and loads. The electrical circuit is described by Ohm's and the Kirchhoff's laws. Ohm's law. I equals V over R. Current flowing through the conductor across 2 points is directly proportional to the voltage and inversely proportional to the resistance of the conductor where it flows. The value of the current flowing between 2 points of a circuit depends on the potential difference between these 2 points and the resistance of the material through which it flows, which results from Ohm's law. For the same, constant resistance, when the potential difference between 2 points of the circuit increases, more current can flow because the higher potential pushes the current with greater force, and the resistance between the 2 points can be overcome more easily. As the potential difference between 2 points in a circuit increases to a point where it reaches a critical value for the maximum current flow through the resistance, the current not encountering sufficient resistance begins to increase rapidly, generating heat that damages the circuit and causes it to break. From Ohm's law, I equals V over R. If V, volts, increases to the critical point infinity, with constant R, resistance. I, current, also tends to infinity. Example: 1 ampere equals 1 volt divided by 1 ohm. The resistance is constant 1 ohm. And voltage increases from 1/10 of a volt to 10 volts and to 100 volts. The current is 1/10 of an ampere for 1/10 of a volt, 10 amps for 10 volts, 100 amps for 100 volts, when the resistance is constant 100 ohms, and voltage increases from 1/10 of a volt to 10 volts and to 100 volts. The current is 1/1000th of an ampere for 1/10 of a volt, 1/10 of an ampere for 10 volts, 1 ampere for 100 volts. As the potential between 2 points in a circuit decreases, the force pushing the current to flow decreases, and the current also decreases until it stops flowing. If there is no potential difference, when the potential difference between 2 points in a circuit is constant, but the resistance between them increases, the current flow will become less and less because the force is too weak to push the current out and overcome the increasing resistance. If the resistance increases to a value at which current is near zero, the circuit between the 2 points becomes like an open path for that current. If resistance increases to the critical point infinity with constant volts, the current tends to zero. Example: 1 ampere equals 1 volt divided by 1 ohm. The voltage is constant 1 volt, and resistance increases from 1/10 of an ohm to 10 ohms and to 100 ohms. The current is 10 amps for 1/10 of an ohm, 1/10 of ampere for 10 ohms, 1/100th of an ampere for 100 ohms. The voltage is constant 100 volts, and resistance increases from 1/10 of an ohm to 10 ohms and to 100 ohms. The current is 1000 amps for 1/10 of an ohm, 10 amps for 10 ohms, 1 ampere for 100 ohms. As the resistance decreases between 2 points in a circuit to the point where it reaches a critical value for the maximum current through that resistance, the current, not encountering sufficient resistance, begins to increase rapidly, generating heat that damages the circuit and causes it to break. Current, potential difference, and resistance in a circuit are interdependent and must always be properly balanced to ensure that critical points are not exceeded for the electrical circuit and that circuit is not damaged. According to Ohm's law, voltage is the amount of current flowing through 2 points of a conductor multiplied by its resistance. V equals I times R. Resistance is the voltage across the 2 points of the conductor divided by current flowing through it. R equals V over I. Kirchhoff's laws. Sigma I in equals sigma I out. Kirchhoff's current law. Sum of the total current entering into a circuit node, junction, is equal to the sum of the current leaving that node. The sum of the currents in the node is therefore zero. The total current entering a node is the same as the total current leaving that node. For example, current 1 equals 12 amps and current 2 equals 8 amps enter the node, while current 3 equals 2 amps, current 4 equals 6 amps, current 5 equals 8 amps, current 6 equals 4 amps. Leave this node. The sum of the current entering the node is 20 amps. And sum of current leaving this node is also 20 amps. Analysis of an example circuit for Kirchhoff's current law. In the nodes of the circuit, the sum of current is: in the node 1, current I1 is equal to the sum of currents I2, I3, and I5. In the node 2, current I3 is equal to the sum of currents I4 and I6. In the node 3, sum of currents I2 and I4 is equal to the current I9. In the node 4, sum of currents I6 and I9 is equal to the current I8. In the node 5, sum of currents I5 and I8 is equal to the current I7. For power source, the current flowing out of a power source I1 is equal to the current I7 returning to that source. Kirchhoff's voltage law. Sigma V equals 0. Total voltage drops and rises in any closed loop in a circuit is 0. Total voltage drops and rises when current flow through the loads in any closed loop in a circuit is 0. Examples of calculation: when the power source is 70 volts and the current from that source is 1 ampere, the voltage across each load in a closed loop in the circuit will be as calculated from Ohm's law for the voltage. Voltage equals current times resistant. When load 1 has a resistance, R, of 10 ohms, and a current, I, of 1 ampere flows through it, the voltage, V, across the load will be V equals I times R1, equals 1 ampere times 10 ohms, equals 10 volts. For load 2 with resistance 20 ohms, the voltage is V equals I times R2, equals 1 ampere times 20 ohms, equals 20 volts. For load 3 with resistance 10 ohms, the voltage is V equals I times R3, equals 1 ampere times 10 ohms, equals 10 volts. For load 4 with resistance 30 ohms, the voltage is V equals I times R4, equals 1 ampere times 30 ohms, equals 30 volts. The sum of the total voltage across each load is 10 volts plus 20 volts plus 10 volts plus 30 volts equals 70 volts. The sum of the total voltages across each load is the same as the voltage of the power source. So the balance of the voltage in the closed loop in the circuit is 0. 70 volts across the loads less 70 volts on the power source is equal 0. In other words, the sum of the closed loop voltage drops and rises across the loads. is always the same as the supply voltage. Another example of a calculation where the voltage of the power source and the resistance of each loads in the closed-loop circuit are known, but the current is not known, and the voltage across each load must be calculated. To calculate the voltage across each load, it is necessary to know the current, which can be calculated using Ohm's law. Current equals voltage over resistance. To determine the current flowing through the loads, add the resistance of all loads, which is resistance load 1 plus resistance load 2 plus resistance load 3 plus resistance load 4 equals 10 ohms plus 20 ohms plus 10 ohms plus 30 ohms equals 70 ohms. And then calculate the current using Ohm's law. I equals V power source divided by R total equals 120 volts divided by 70 ohms equals approximately 1.71 ampere. Approximately, because there are more numbers after the whole number. Knowing the current, you can calculate the voltage across each load using Ohm's law as follows. Voltage, V, across load 1 equals current times resistance load 1 equals approximately 1.71 amps times 10 ohms equals approximately 17.1 volts. Voltage, V, across load 2 equals current times resistance load 2 equals approximately 1.71 amps times 20 ohms equals approximately 34.2 volts. Voltage, V, across load 3 equals current times resistance load 3 equals approximately 1.71 amps times 10 ohms equals approximately 17.1 volts. Voltage, V, across load 4 equals current times resistance load 4 equals approximately 1.71 amps times 30 ohms equals approximately 51.3 volts. The sum of the total voltages across each load, approximately 17.1 volts plus approximately 34.2 volts plus approximately 17.1 volts plus approximately 51.3 volts equals approximately 120 volts. Is the same as the voltage of the power source, 120 volts. So the balance of the voltage in the closed loop in the circuit is 0. In the closed loop in the circuit, the load resistance is in series, and the same amount of current flows through it. When the load resistance is connected in parallel or mixed, series and parallel, the calculations look different. Example calculations for Kirchhoff's voltage law in a mixed resistance connection, parallel and series. The voltage of the power source is known, as well as the resistance of each load. Power source voltage is 120 volts. The resistance of the load 1 equals 10 ohms. Load 2 equals 50 ohms. Load 3 equals 20 ohms. Load 4 equals 10 ohms. And load 5 equals 30 ohms. In parallel connection, the voltage across each load is the same as the voltage of the power source. The voltage across load 4 and load 5 is calculated using Ohm's law in the same way as in a closed loop in the circuit, series connection. When the current flowing through both loads is known, this current is the same for all loads in series circuit. To calculate the current flowing through load 4 and load 5 in series connection, add the load resistances and calculate the current using Ohm's law, as in the parallel connection for one resistance. The voltages of the parallel connected loads are equal to the voltage of the power source. Voltage 1 load 1 equals voltage 2 load 2 equals voltage 3 load 3 equals voltage 4 load 4 plus voltage 5 load 5 equals voltage of the power source. To find the current drawn from the power source, calculate the current in each branch using Ohm's law. Current load 1 equals voltage power source divided by resistance load 1 equals 120 volts divided by 10 ohms equals 12 amps. Current load 2 equals voltage power source divided by resistance load 2 equals 120 volts divided by 50 ohms equals 2.4 amps. Current load 3 equals voltage power source divided by resistance load 3 equals 120 volts divided by 20 ohms equals 6 amps. Current load 4 and load 5 equals voltage power source divided by resistance load 4 plus resistance load 5 equals 120 volts divided by 10 ohms plus 30 ohms equals 120 volts divided by 40 ohms equals 3 amps. The total current from the power source is the sum of the currents of each load and is current load 1 plus current load 2 plus current load 3 plus current load 4 and load 5 equals 12 amps plus 2.4 amps plus 6 amps plus 3 amps equals 23.4 amps. The return current to the power source is always the same as the current leaving that power source. More complicated calculations occur when we mix the same loads in the circuit, as shown in the example drawing. The voltage of the power source is known, as well as the resistance of each load. Power source voltage is 120 volts. The resistance of the load 1 equals 10 ohms. Load 2 equals 50 ohms. Load 3 equals 20 ohms. Load 4 equals 10 ohms. And load 5 equals 30 ohms. The sum of the voltages of the parallel connected loads is equal to the voltage of the power source. Voltage 1 load 1 equals voltage 3 load 3 equals voltage 2 load 2, load 4 and load 5 equals voltage of the power source. To find the current drawn from the power source, calculate the current in each branch using Ohm's law. Current load 1 equals voltage of the power source divided by resistance load 1 equals 120 volts divided by 10 ohms equals 12 amps. Current load 3 equals voltage of the power source divided by resistance load 3 equals 120 volts divided by 20 ohms equals 6 amps. To calculate the current in the branch with load 2, load 4, and load 5, the voltage across load 4 and load 5 must be known. To determine the current flowing in this branch through load 2, you need to know the voltage across load 2, which is the power source voltage, less the voltage across load 4 and load 5. Voltage load 2 equals voltage of the power source less voltage load 4 and load 5. To find the voltage across the load 4 and load 5, the current flowing in load 4 and load 5 must be calculated. To find the current flowing in load 4 and load 5 with an unknown voltage across them, you must know the total resistance of load 4 and load 5, which can be calculated using the equivalent formula for calculating the total resistance in a parallel connection. The formula for equivalent resistance is resistance equivalent equals 1 over 1 divided by resistance 1 plus 1 divided by resistance 2 plus 1 divided by resistance 3 plus 1 divided by resistance if it is more resistances in parallel. Equivalent resistance for load 4 and load 5 is resistance equivalent equals 1 over 1 divided by resistance load 4 plus 1 divided by resistance load 5 equals 1 over 1 divided by 10 ohms plus 1 divided by 30 ohms equals 1 over 1/10 of an ohm plus 33 thousandths of an ohm equals 1 over 133 thousandths of an ohm equals 7.52 ohms. The current flowing through the load 2 is equals voltage of the power source divided by resistance load 2 plus equivalent resistance of load 4 and load 5 equals 120 volts divided by 50 ohms plus 7.52 ohms equals 120 volts divided by 57.52 ohms equals 2.09 amps. The voltage for load 4 and load 5 equals current load 2 times resistance of equivalent load equals 2.09 amps times 7.52 ohms equals 15.72 volts. Current load 4 equals voltage load 4 and load 5 divided by resistance load 4 equals 15.72 volts divided by 10 ohms equals 1.57 amps. Current load 5 equals voltage load 4 and load 5 divided by resistance load 5 equals 15.72 volt divided by 30 ohms equals 0.52 amps. The total current from the power source is the sum of the currents of each load and is current load 1 plus current load 3 plus current load 2 equals 12 amps plus 6 amps plus 2.09 amps equals 20.09 amps. The return current to the power source is always the same as the current leaving that power source. More basic knowledge about electricity that is worth having before starting work related to electrical installation or other work related to electricity. There are two basic types of current: direct current, DC, and alternating current, AC. Direct current, DC, flows in one constant direction. Alternating current, AC, periodically changes direction and produces a sine wave. Direct current, DC, is used to power electronic devices and other household appliances after the alternating current is converted to direct current using rectifiers in these devices. Alternating current, AC, powers homes and comes from power plants owned by utility companies or small, individual power plants located near homes, solar panels, wind turbines, etc. The number of complete cycles of an AC sine wave in 1 second is called the frequency and is measured in Hz, Hz. In the US this is 60 Hz. The alternating current supplied to homes flows from the power plant through a substations to a transformer located near the house, and from there to an electricity meter on or in the building. and then to a distribution board that distributes the electricity throughout the house. What are you really paying for when your electricity meter counts the energy used in your home? When you look at your bill from your electricity supplier, you see that you pay per kilowatt hour. How much energy is 1 kilowatt hour? 1 kilowatt hour is 1000 watts that any household appliance consumes during 1 hour of its operation. Power, in watts, is the amount of work done by electricity. The formula for power comes from Ohm's law and states that power, watt, equals voltage, volt, multiplied by current, ampere. 1 watt equals 1 volt times 1 ampere. Example: knowing the power of an electrical device or equipment, you can calculate how long it must operate to consume 1 kilowatt-hour of energy for which you must pay. How long does a 10 watts bulb have to operate to consume 1 kilowatt-hour of energy? 10 watts bulb uses 10 watts per hour. So a 1 kilowatt will be used in 1000 watts divided by 10 watts equals 100 hours. 10 watts bulb must operate for 100 hours to consume 1 kilowatt of energy. Knowing the power and voltage of this light bulb, 120 volts, you can easily calculate the current consumed by this device, transforming the formula. Power equals voltage times current. So the current is equals power over voltage. For 10 watt light bulb at 120 volts, the current is current equals power divided by voltage equals 10 watts divided by 120 volts equals 83 thousandths of an ampere. If the current and power are known, the formula is voltage equals power over current. Power is power, so watt is a watt, regardless of voltage and current. An electrical device or equipment must use the same amount of energy to do the same job. The same 10-watt light bulb powered by 10 volts or 1000 volts will consume the same amount of energy, only the current flowing through it will be different, lower at a higher voltage or higher at a lower voltage. Power is voltage times current. For 10 volts, the current is current equals power over voltage equals 10 watt divided by 10 volts equals 1 ampere. For 1000 volts, the current is current equals power over voltage equals 10 watt divided by 1000 volts equals 1/100th of an ampere. All of the electrical laws and formulas presented are essential when wiring a home to properly select the cables, overcurrent protection, etc. that power home electrical appliances. The electrical installation in homes is regulated and described by the NEC, National Electrical Code, and all calculations contained therein regarding current are based on the presented formulas.